All right. Hello, 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 hello. Thank you for letting me know. We're going to be talking about artificial intelligence, architecture, algorithms, and the path of superintelligence. Um, I want to begin with a thought experiment. I have to repeat this for everyone else, not for TikTok. Because it was not coming out the audio in other streaming. So I want to begin with the thought experiment. Imagine you are sitting in a university library in 1936. Across the table from you is 24 years old graduate student at Cambridge. He's not particularly famous. He has published nothing yet. He's working on a paper about a hypothetical machine, a machine that reads symbols from an infinite tape, move left and right, writes new symbols and halts when it reaches a final state. He calls it a universal computer machine. His name is Alan Turing, and the paper he's writing will establish in 8 pages a dense mathematic, the theoretical foundation for every computer that has ever existed, every algorithm you have ever run, every neural network you will hear about tonight, including the systems they are right now beginning to write their own code. Reason about novel problems and approach what we might call, with appropriate caution, general intelligence. So, right now, tonight, happening right now, we have machines. They are writing codes by themselves. Many years ago, we needed software programmers, software coders to do this. Tonight, we have machines doing this by themselves. Okay? So, I want for you to start getting that to see the difference of how everything is shifting from how things were before to where things are going to be. Okay? I choose to begin there because I want you, everybody, that is watching. I have developers, researchers, engineers, scientists, everyday person, people with different backgrounds, education, no education, learning, starting to learn, student college, high school, all the way to retirement people are watching these through TikTok, YouTube, Kick, um, X, everywhere. Um, I'm choosing to start this here. I have to do something on different platforms as well. So I'm going to be working on the computer as well for just a little bit, so I can get everything going. Um, hey, hello, how are you? Welcome, welcome. So I need to see. Yes, they're still doing it. Um, mm, right. So we're sending in a message at x.com. Something happened that the guys from the Department of Homeland Security that don't like me doing what I'm doing. They are very envious and very short-minded, and obviously they copy a bachelor's degree. They see this as a joke for them, but this is very important for everyone as we move forward here at Because when I used to post from my streaming channels, a message will come out directly. Now that is blocked, I need to find out why that is happening, but we'll look for that in another time. This is not important right now. Um, uh, right. So I choose to begin here because I want you a room. Okay, I want you I want you to start here. It's just like a lot of people, like from developers, researchers, engineers, scientists, data scientists, people that are involved in the segment of artificial intelligence, computing, servers, architecture, etc., 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 to understand that the story we're living through is not new. It's a continuation of the longest running technical project in the history of science. The attempt to make machines that think, and we are in the inflection point. Not the beginning, not the end, the inflection point. The moment where the curve stops being gradual and becomes, in a mathematical sense, nearly vertical. We got rockets, baby. We're going up, all the way up, okay? Over the next few hours, I am going to take you through the entire arc of that story, from turning state to transform our attention mechanism, from the perception and perceptron of GPT-4, from Marvin Minsky optimism to Geoffrey Hinton's Nobel Prize and his public warnings about extinction risk. And then in the final hour, I am going to take you to the frontier, to AIG, to superintelligence. That's very important, to the alignments problem. And I am going to be completely honest with you about what we know, what we don't know, and what the stakes actually are. I'm going to assume that you are technical, sophisticated. I'm going to use the real vocabulary: backpropagation, stochastic gradient descent, attention heads, KV cache, RLHF, uh, constitutional AI, mess optimizations, instrumental governance. If a term is unfamiliar, stay with me. I will define everything as I introduce it, but I will not dumb this down, okay? Uh, I know you guys are very smart. You guys been with me in this account and other past accounts, and everybody that is watching and following me is been getting educated. They are not beginners now. We have new developers, a class of 2025. We have new people with new frontiers that they have done it that by themselves. So if you have take that route, I'm very proud of you that you have decided to do something different with your life. So let's start. Okay, the mathematical and historical foundation, computability, church, and Turing machine. Okay, to understand AI, you must first understand computation, what it means firmly and precisely for a process to be computable. This is not a philosophical question. It is a hard mathematical one, and it was answered. They independently and simultaneously by two people in the mid 1930s. For be exact, 1936, 1937. The first was Alonzo Church of Princeton, who in 1936 developed lambda calculus, a formal system for expression computation in terms of function abstractions and application. Church proved the undisability of the anti-Stolz's problem, Hilbert's famous decision problem, which asks whether there exists a general algorithm that can be determine the truth or falsehood of any mathematical statement. The second was Turing, who developed his model independently and arrived at the same conclusion. His proof used different and arguably more intuitive construction. The machine that reads and writes symbols on tape, Turing machine is formally defined as a 7 tuple M and a finite set of states, Q, I, B, E, Q, F, etc., to the cube. A tape alphabet, a blank symbol, input, symbols, and transition functions, an initial state and set of final states. The machine reads a symbol transition to a new states, write the symbols, and move the head left or right. Church and turning together establish what we now call the church turning tests, a function that can be computed by an effective procedure by any physical device operating according to deterministic rules can be computed by a Turing machine. The stored program computed the von Neumann architecture emerged directly from this insight. Every computer you have ever used runs in a variant of this architecture. The line from Turing abstract machine to your CUDA kernels is directly unbroken. Now I want to dwell on the halting problem for a moment because it has direct bearing on AI. The halting problem states there is no general algorithm that can determine for an arbitrary program P and arbitrary input I whether P will halt or run forever. Turing proof is a beautiful diagonal argument. Assume a machine H solve the halting problem, construct, construct a machine D that contradicts H answers about itself and arrive at a contradiction. Therefore, H cannot exist. Why does this matter for AI? Because if an AI system is turning complete, there will always be questions about its behavior that cannot be answered by examining its code. You cannot always determine in advance what sufficiently powered program will do. This has deep implication for AI safety and the alignment problem, which we will address in the next few hours. The birth of AI, Dartmouth 1956 to the first AI winter. In the summer of 1956, a group of researchers gathered at Dartmouth College, among them John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon. McCarthy coined the term that will define the field, artificial intelligence. The Dartmouth workshop established the symbolic AI hypothesis. The intelligence is fundamentally the formal manipulation of symbols according to rules. Early results were genuinely impressive. The logic theorists proved 38 of the 52 theorems in Principia Mathematica. Elisa simulated a physiotherapist so convincingly that users formed a genuine emotion attachment to it. Users who knew perfectly well it was a program might seem diagnose bacterial infections using 600 IF then rules at levels matching specialist physicians. XCON configure VAX computer systems and save Digital Equipment Corporation estimated $25 million per year. But their fundamental problems were insurmountable. First, the knowledge acquisition bottleneck. Beautiful bottleneck that we're still dealing with, but sooner or later we're gonna not have more bottlenecks, okay? Building an expert system requires extracting knowledge from human experts and encoding it in rules. A slow, expensive, and imperfect process, experts often cannot articulate their own knowledge. Michael Polanyi had identified this as a tactic knowledge problem. AI researchers discovered it empirically and painfully. Let me see if I can all right. Um, First, the knowledge acquisition. Second, the brightness problem. Expert systems fail catastrophically outside their training domain. There was no common sense, no ability to reason from first principles, no robustness to unexpected inputs. Third, and most fundamentally, the frame problem, formalized by McCarthy and Hayes in 1969. How does a system knows what does not change when an action is performed? In the real world, when you pick up a cup, the cup's position changes, but the color of the walls does not. Talking about a cup, time for a little sip of nice, beautiful coffee. How about that? Symbolic system must explicitly represent which fact remain unchanged by each action. And as the number of facts and action grows, this becomes computationally catastrophic. The AI winter followed. The first beginning around 1974 with the Lighthill Report in the United Kingdom, the second in the late 1980s when expert system company collapsed. But AI did not die. It went underground. Real underground. Yeah, baby. And from that period came the research threads that will produce the revolution we're living throughout now. Okay? We're going now to move to the statistical turn. Machine learning emerges. The shift that changed everything was philosophical. Instead of encoding intelligence top down as rules, what if we allowed a machine to learn bottom up from the data and experience? The central development was the rediscovery and popularization of backpropagation by Roman Hart, Hinton, and Williams in the landmark in 1986 Nature paper. The algorithm applies the chain rule of calculus recursively from the output of a network back to its inputs, computing the gradient and the laws with respect to every parameter. The update rule is simple. It's an equation. Okay, I will put all these equations down below on all the social medias. So I'm not going to complicate this, so it's not hard for everyone. Okay, but the consequence was profound. Multi-layer neural network could learn their own internal representation of data without being told what those representations should be. The hidden layer developed meaningful features automatically. This was not programmed, it emerged from training. So I'm thinking probably I own the equation agency LLC, and I am going to put all these equations on a website that I am going to be building, so like everybody can learn about these equations. So we'll have like a separate area on the equation agency LLC website, which I need to like build it up, and I'm going to put all these equations in an area so like people can learn about some equations. Okay. The hidden layers develop meaningful features automatically. This was not programmed, it emerges from training. Despite this theoretical advance, the 1980s were dominated by support vector machines, Vapnik and Cortez 1995, and ensemble methods like random forest and gradient boosted trees. They outperformed neural networks on most benchmarks because they were better matched to the computational resources available. The question was never whether neural networks could learn powerful representations. The 1986 paper had proven they could. The question was whether they could be trained efficiently to enough on data at sufficient scale. The answer came in 2012, and it came from hardware. Moving to the next section is the image net moment and the GPU revolution. Here's when they come the GPUs, okay? Things are starting to get faster and more faster thanks to the GPUs revolution. Fei Fei Li's ImageNet dataset, 1.2 million labeled images across 1,000 categories, and the annual ILSVRC competition, providing the proving ground. In 2010, the best error rate was 28.2%. In 2011, 25.8%, incremental steady progress. Then came 2012, Alex Krinsvisky, Ilya Sutskever, and Geoffrey Hinton submitted AlexNet, trained on two NVIDIA GTX 580 GPUs. Top 5 error rate 15.3%. So we as years climb, okay, um, the error rate declines. So years go, error declines. Okay. Next best entry, 26.2%, a margin of nearly 11 percentage points that the entire field had not expected to see for another 5 or 10 years. AlexNet demonstrated several techniques now standard practice, relay activation with the equation Fx times equal max times Ox, which avoid the vanishing gradient and train 6 times faster than tan. Dropout regularization at p equals zero point 0.5 on the fully connected layers, data augmentation and GPU training delivering roughly 4 times throughout the CPU training. The network has 60 million parameters across 5 convolutional layers and 3 fully connected layers. The cascade of results that followed was extraordinary. VGGNet showed depth matters. GoogleNet introduces multi-scale inception models. ResNet's um, he he AL 2015 introduced keep in connections with another equation h times x equals f times x plus x, allowing gradient to flow directly across layers and enabling 52 layers networks. Finally, ImageNet's top errors 3.57% below the estimated human error rate approximately 5%. The machine had learned to see better than we could, and the rate had only just begun. Okay, so as we move in years, the years go up, and the percentage of error, things are starting to get more perfect with the years that come. Okay, now we're gonna talk about the Transformer Revolution and the LM era. Sequence modeling before transformers. Give me 1 second here. Uh, okay. All right. So the Transformer Revolution and the LM era. Sequence modeling before transformers. Language is inherently sequential. The dominant approach through the 2010 was the recurrent neural network. An RNN processes a sequence one token at a time, maintaining a hidden state. HT equals TH and H ton, and the equation is WHH HT minus 1 plus WXH times X. The problem is backpropagation throughout multiple by the Jacobian of the hidden state. If the vector radius of WHH is less than 1, gradient vanishes exponentially. If greater than 1, they explode. R and N's fails to learn dependencies across more than roughly 10 to 20 time steps. LSTMs, Hochreiters, and Schreimoter on 1997 introduced gating mechanisms. A forget gate. It has another equation, F equals O, WF times H T minus 1 times H times XT times plus BF. An input gate and sales state that acts as an information highway across many steps. This was a significant improvement, but the fundamental bottleneck remained. The bottom bottleneck continues to remain. So as you can see, this is like a uh, we have we've been dealing with bottlenecks all our lives, and eventually, there will be no bottlenecks, and we're getting very close to that part. Okay. Um, but now, no attention in 2015 partially addressed this. The decoder could look back at all encoder hidden states and compute a weighted sum. But the encoder and decoder were still RRNs. The sequentially dependency remained. Okay, in 2017, Vaswani, Shazir, Parmar, Uskororetic, Jones, Gomez, Kaiser, and Poluskin published a paper with a deliberately provocative title: Attention is all you need. Their claim recurrence is necessary. I don't know. Attention. Attention is all you need. Just give me 1 second. Let me just open something for someone. Fue otra persona. Sí. So, um, let's see. In 2017, Wassini Cherser, Parmar, Ukuseki Jones, Gomez Casier, and Polunitsky published a paper with deliberately provocative title: Attention is all you need. Their claim, uh, recurrences is unnecessary. Attention alone, applied in parallel across the entire sequence, is sufficient. They were right. The fundamental operation is scale dot product attention. Attention KVV equals softmax K QKT divided VDK and V. Unpack this precisely. Queries Q and keys K compute compatibility scores. The dot product QKT give entry IJ as the similarity between query I and key. Pushing softmax into low gradient regions. Softmax converts scores to attention weight summing to 1. We take a weight sum of values. V, every token simultaneously acts as a query, a key, and a value. Every token can directly attend to every other token. No sequential dependency, no vanishing gradient, no information and bottleneck. Multi-head attention runs H parallel attention operations with different learn projections. Multi-head QKV equals concat, head and head, and WO, allowing the model to attend to multiple aspects context simultaneously. In GPT-3, the model equals 12,288 heads. DK equals 128 points. Computational complexity is O times N2 times D. In sequence length, the quadratic scaling that makes long context expensive. A flash tension by Dow et al. 2022 archives the same mathematical result with O times n. Memory by recording computation to minimize memory bandwidth usage. Positional encoding addresses the fact that attention is permutation equivariant. The original sinusoidal approach, PE-POS2I equals SIN times POS divided by 10,000 times at 2I times divided D underscore model times period. Modern models use ROP rotary positioning embeddings or alibi. A full transformer block, multi-head self-attention, residual connection, plus layer norm. Position wise feed forward network. Residual connection, plus layer norm. Encoder only. BERT. Process bidirectional decoder only. GPT uses capsule masking. Each token attend only to previous tokens. Virtually all frontiers models today, GPT-4, Claude, Gemini, Llama, are decoders only transformers. Scaling laws and emergent capabilities. In 2020, Kaplan, McCandish, Hennigan, and colleagues at OpenAI published scaling laws for neural language models. Performance follows Muth-Powers laws across many order of magnitudes, and we continue to get more equations. For a fixed computer budget, optimal location in parameters and in tokens. The Chinchillaya paper, Hoffman et al. And DeepMind in 2022 revised these ratios and D should scale equally, approximately 20 tokens per parameter. GPT-3 at 175 billion parameters trained on a 300 billion token was undertrained by his standard Llama 2 at 70 billion parameters trained on 2 trillion token. Ishinkiaya optimal GPT-3 training costs an estimated 5 to 10 million dollars. GPT-4 is estimated at $100 million or more. The scaling law paper gave AI labs a clear empirical rationale for investing in ever larger training runs. If loss follows a predictable power law, larger models will reliably perform better with no hard silicon visible at current scales. Emergent abilities. Wei et al. 2022 documented capabilities appearing discontinuously at threshold scales. Multi-step arithmetic, logical deduction, analytical reasoning, program synthesis, chain of thought reasoning emerged around 100 billion parameters. In context, learning emerged at the few billion. The interpretation is condensed. Schaefer uh, 2023 argues emergence is an artifact of discontinuous metrics, but the patriarchal phenomenon is not. Scanning reliability produces new capabilities, often unanticipated. Section Next section: instruction tuning and RLHF. A pre-trained language model predicts the next token. It has no concept of helpfulness. The transformation to a useful assistant required two stages. First, a supervised fine-tuning on human-written prompt response demonstration with algorithm 2021 show instruction-tuned models generalize zero-shot to instructions not seen during fine-tuning, outperforming much larger base models. Um, Second, reinforcement learning from human feedback, RLHF. Three stages collect comparison data. Human raters compare response for given prompt. Train reward model, RO, of those preferences using the objective mass. Then optimize the language models against the reward model via PPO with the KL divergence penalty. So it's max E times RO times x comma y minus uh, b times kl and pi times x parallel tsft times x. The KL penalty prevents the model from drifting too far from its supervised fine-tuned behavior, preventing reward hacking. The PPO clip objective limits excessively large policy updates. The Instruct GPT paper showed a 1 3 billion parameter RLHF model was preferred by human evaluators over the raw 175 billion parameter GPT-3 on the vast majority of prompts. Alignment training dramatically improves perceived quality even when it reduces raw parameter count. Capabilities and alignment are not in fundamental tensions. Constitutional artificial intelligence anthropic approach adds a set of written principles to the process that model critiques and revises its open output accordingly to those principles. AI feedback, RLAIF, scales better than pure human evaluation. ChatGPT launched on November 2022, 1 million users in 5 days, 100 million in 2 months. No consumer technology in history had ever grown that fast. Okay, so the multimodal models and scientific AI. Hey, how you doing, everybody? On okay. Um, the current frontier, multimodal models and scientific artificial intelligence. The transformer architecture generalized beyond text. Any sequence of tokens will do image patches, audio spectral frames, video frames, protein residues. This architecture universally has produced multimodal models that process and generate content across modalities in an integrated way. Clip Radford algorithm at OpenAI on 2021 trains images and text encoders jointly using contrastive learn contrastive learning maximize cosine similarities of machine image text pairs while minimizing non-matching pairs. The result is a shared embedding space where images and their descriptions are geometrically close. Zero shot clip match fully supervised. Next, uh, ResNet 50 on ImageNet without a single label image. The rich semantic structure of language alone provides sufficient supervisory signals. Diffusion models generate images by learning to reverse a noise process. The forward process, and there's another equation, xt equals va times x 0 plus v 1 minus a to the t, and e progressively adding Gaussian noise. The model learns to predict the noise and at reference start from pure noise and interactively denoise conditions on a text prompt. Classifier free guidance. Higher W gives image more faithful to the prompt. Latent diffusions minus stables diffusions minus operate in VAE compressed latent space 4 to 8 times more efficient than a pixel space diffusion. AlphaFold 2 jumper EAT algorithm, Nature 2021, solved the protein folding problem using the evoformer architecture. It processed multiple sequence alignments, related sequences from across evolutions, along with pairwise distant features, updating both in a quadruple way. The intuition evolution performed a massive natural experiment and covariation patterns across species encode three-dimensional structures constraint. TM score of 0.92 on Cas14. The database now contains predictive structure for over 200 million proteins, essentially ever known protein. The implications for drug discovery are most significant scientific achievement of this century. So, with these equations and all these algorithms, the AlphaFold and the jumper algorithm, we're going to have more achievements on the scientific area of on this century. Okay, agentic AI and autonomous systems. Okay, this is what is coming next. We're starting to see those agentic AI autonomous systems. We start see vehicles driving themselves, boats will drive themselves, airplanes will drive themselves, everything will drive themselves. Okay, robots will walk by themselves. Um, a language model that answers questions is impressive. A language model that plans a sequence of actions, use tools, observe results, and revise its plan in pursuit of a goal is something qualitatively different. The React Loop Yao It algorithm 2022 interleaved throughout traces and actions invocations. The model reasons about what to do next, you know. It generates a structured tool calls or receive the observation, incorporates it, and continues and continues. Tools used via function calling structured JSON schemas define variable tools. The model generate calls and a sandbox execute them. Results return in an observation, code execution. The models write Python. The interpreter runs it, stands out, and stay there. Return as the next observation. Multi-agent system decompose tasks across specialized agents operating in parallel pipelines. Orchestrator sub-agents architectures. A central agent decomposes the task and delegates, and reliability compounds across agents. Five agents, each at 90% per task, give only 59% overall success. Remember, these are new things. As we move forward, the overall success, 59%, will start coming down as well. Okay. Context window management and memory architecture require explicit engineering. The retrievable augmented generation grounds models in real data documents are encoded as dense embeddings stored in vectors databases, Pinecone, Vivitate, Chroma, and PG vectors, and retrieved at inference time by cosine similarity research. Retrieved documents are injected into the context windows alongside the query. Advanced rank pipelines add query rewriting, hypothetically document embedding, re-ranking, and recursive retrieval to improve quality and reduce hallucinations. The current model landscape and benchmarks. GPT-4 from OpenAI is an estimate mixture of experts architectures, 128,000 tokens context windows, top performance on month, human evaluation, and MMLU. GPT-4 meaning integrate text, vision, and audio end to end rather than top modular pipelines. Claude 3.5 Sonnet, philanthropic state of the art on SW Bench, resolving approximately 40 to 50% of real GitHub issues. Strong instruction following constitutional AI alignment and active mechanism interpretability research. Gemini Ultra from Google DeepMind first model to exceed human expert performance across all 57 MMLU subjects, natively modeled from the ground up. So the 57 MMLU subjects are abstract algebra, anatomy, astronomy, business ethics, clinical knowledge, college biology, college chemistry, college computer science, college mathematics, college medicine, college physics, college security, conceptual physics, econometrics, electrical engineering, elementary mathematics, formal logic, global facts, high school biology, high school chemistry, high school computer science, high school European history, high school geography, high school government and politics, macroeconomics, mathematics, microeconomics, physics, psychology, statistics, U.S. history, and world history, human aging, human and sexuality, international law, jurisprudence, logical fallacies, machine learning, management, marketing, medical genetics, miscellaneous moral disputes, moral scenarios, nutrition, philosophy, prehistory, professional accounting, professional law, professional medicine, professional psychology, public relations, security studies, sociology, U.S. foreign policy, virology, and world religions. So, is one of these are your jobs? Know that you are will be replaced, and you are currently already will be replaced by artificial intelligence in the next 10 years, 5 to 10 years, because um, that's where we at right now. Um, the Llama 3 from Meta, 70 billion open weight parameters competitive with significantly larger closed model. The existence of powerful open weight model has profound implications for research, accessibility fine-tuning, and the competitive dynamics of the industry. Benchmarks MLLU text knowledge across 57 subjects, the subjects that I just mentioned. GPT-4 scores approximately 87% human expert and approximately 89% random baseline, 25% human evaluation measure code generations. So GPT-4, and now we are in GPT 5.2, and we're going to be continue moving up. As we continue moving on models, um, GPT-4 scores approximately 87%. Okay, and human expert approximately 89%. That's B plus on all 57 subjects. Okay, um, humans are expert on few of those subjects. This is scoring overall 89% on GPT-4. Now we are on GPT-5. So what happens every time that we move from one model to a new model? The model goes up, and 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 the percentage of the human experts continues to go up. Okay, so what was B plus becomes A minus, and after A minus becomes A plus, and after A plus comes super intelligence. Okay, human evaluation measure code generation. GPT-4 achieved pass at one of approximately 67%. So SWE bench measure practical software engineering capabilities. Frontier models solve 40 to 50% of verified tasks. ARC uh, AGI, designed to require genuine abstract reasoning, was below 20% for all frontier models until Mini 3 achieved 87.5% at high compute. Critical caveat: benchmark uh, performance and real world utility are imperfectly correlated. Goodhart's law applies. A measure that becomes a target ceases to be good measure. Treat benchmarks numbers as signals, not ground truth. Okay. So the benchmark numbers are just signals. Okay. So and the signals are that as we continue to move models and the models and the computers continue to evolve and continue to learn, continue to get better, um, what they failed last year, they already learned it. They're not going to commit the same error. So they're going to continue to move forward. Artificial intelligence in production, infrastructure, and inference engineering. That's the next subject. Training frontier models require thousands of GPUs in tight synchronicity. Distributed training strategies, data parallelism, replicates the model and split the data batch. Model parallelism splits the model itself across devices when it does not fit in a single GPU's memory. Tensors parallelism splits individual matrix operations. Pipeline parallelism splits into layers into stages. Numerical precisions, FP32 for stability, FP16 and BF16 for training efficiency, INT8 and ANT for quantization for inference cost reduction. The KV cache store keys and value projections from all previous process tokens, enabling efficient autoaggressive generations without reprocessing the full context at each step. Imagine managing KB cache memory across thousands of concurrent users require continuous batching and cache eviction and careful memory management. Speculative decoding uses a small draft model to generate candid tokens that the large model then verifies in parallel, achieving 2 to 3 times throughout input improvement. The cost of latency profile of LLM inferences measured in tokens per seconds and dollars per million tokens is a central engineering constraint shaping what applications are feasible. A well-quantized 20 billion parameter open weight model running locally is competitive with cloud API calls for many applications at fractions of the ongoing cost. So when we're talking about F32 for stability, FP16 and BF16 for training efficiency, INT8 and ANT4 quantization for inference cost. We're talking about how numbers are represented inside of the GPUs and neural networks. Neural networks are just large collections of matrix multiplications, matrix or multiplications multiplying and adding numbers and billions and trillions of times. Okay. Um, Give me 1 second. Uh, so, hello, everybody on TikTok. How you doing? So, what is a numerical precision? Computers do not store real numbers like humans write them. They store approximations using binary flotation points or integer formats. The more bits used to represent a number, the more precise it is. The larger range of values it can represent, the more memory it consumes, the lower it may be compute. Precision equal trade-off between accuracy, speed, memory, and cost. So your binary 0, 1, that's what we're talking about here, okay? FP232 and 32-bit floating points is the full precision. 1 bit for sine, 8-bit for exponents, and 23-bit for mantissa. This gives 7 decimal digits of precision, very wide dynamic range, and very strong numerical stability. Why we use FP32? Because training neural networks involve back propagation, very small gradient values, and accumulating tiny updates over millions of steps. If precision is too low, gradients can vanish to zeros, um, and overflow to infinity becomes unsustainable. Hello, I go later on. I go later on to co-host and take all the invites. Okay. The downsides, 4 bytes per parameters slows the GPUs compared to low precision. For a 7 billion parameter model, 7 billion times 4 bytes equals 280 gigabytes just for weights before optimized states. That's massive. The FP16 half precision 16-bit floating point. That's what FP16 means. One sign, 1 bit, 5 exponent bits, 10 mantissa bits. This means much less precision, more smaller range, 2 bits per parameter, half memory of um, floating point 32. Huge advantage. Modern GPUs, NVIDIA Tensor cores, excuse me, are optimized for floating point 16 math, 2 times memory savings, 2 times the output increase. The the problem, smaller exponent range, move to gradient can underflow. Training can become unstable. The solution is a mixed precision training. In mixed precision, for pass in floating point 16, gradients computed in floating point 16, master weight storage on floating point 32, loss scaling prevents underflow. This preserves stability while doubling speed. So BF16's brain floating point, the BF float 16 is different from floating point 16. It uses one sign bit, 8 exponent bits, same as a floating point 32, and 7 mantissa bits, meaning same dynamic range as floating point 32, less precision in detail, 2 bytes per parameter. Why this is powerful? Because most neural networks instability becomes from exponents overflow, underflow, not for mantissa precision. Brain floating point 16 keeps the wide range but reduces detail precision that makes it more stable than floating point 16, lately as fast, easier to train large models with most modern LLM training uses brain floating point 16. While lower precision is important, training a frontier model costs thousands of GPUs, weeks of months of compute, tens to hundreds of millions of dollars. If you can cut memory in half, double the throughput, and reduce energy costs, you change the economics of AI. Precision is not a math choice, it's a financial decision. Uh, INT8, 8-bit quantization inferences. After a model is trained, we usually don't need full precision. During inferences, no backpropagation, no gradient accumulation, just forward pass. We can compress weights from floating points to integers. INT8 means 8-bit integers, 1 byte per parameters, 4 times smaller than floating point 32, 2 times smaller than floating point 16, brain floating 16. To do this, we apply quantization. Original weight W scales times into 8 value. The model stores integer weight scale factor when running INT8 times INT8 accumulate rescales. Modern GPUs support fast INT8 matrix multiplications. Result 2 minus 4 times faster inference, massive memory saving, lower cloud cost. Um, the inch for 4-bit quantization aggressive compression uses 4 bits per parameter, 0.5 bytes per weight, and 8 times smaller than FP32. This is extremely compact, uses for running elements locally, edge devices, consumer GPUs, and mobile hardware. Examples 70B parameters, uh, FP32, 280 gigabytes, BF16, 140 gigabytes, NT8, 70 gigabytes, and NT4, 35 gigabytes. As you can see, gigabytes start going down. So less gigabytes, you have less cost on the server side on the equation. Okay. Now suddenly, consumers' GPUs can host large models. Cloud cost drops dramatically.